Hello all, myself Devendra Itole, working as an assistant professor in ENTC Engineering Department from AISSMS Institute of Information Technology Pune. Today's topic is pulse width modulation of PIC microcontroller. In pulse width modulation mode, the CCP X pin produces up to the 10-bit resolution PWM output. Since the CCP2 pin is multiplexed with a port B or port C data latch, the appropriate trace bit must be cleared to make the CCP2 pin an output. Figure shows the simplified block diagram of CCP module in PWM mode. In diagram, you can see duty cycle register CCP-RXL and CCP-X con 4th and 5th bit moves into the CCP-RXH slave, is compared with the TMR2 value, and TMR2 will compare with the PR2 value. The comparator between the CCP-RXH slave and TMR2 will give the output to the RS flip-flop, and accordingly we are getting the output at Q point. Note, clearing the CCP2 con register will force the RB3 or RC1 output latch to the default low level. This is not the port B or port C input output data latch. PWM output has a time base or period and a time that the output stays high. The frequency of the PWM is the inverse of the period. So we can observe in the diagram, duty cycle period is equals to duty cycle initially TMR2 equals to PR2, at a half after the completion of half cycle TMR2 equals to duty cycle, and after the completion of whole cycle turn on time and turn off time TMR2 will become equals to PR2, and that is called as a period. So PWM period is specified by writing to the PR2 register. The PWM period can be calculated using the following formula. PWM period equals to, in square bracket, PR2 plus 1 multiply 4 multiply by TOSE oscillator timer multiply by TMR2 prescale value. Then PWM frequency is defined as 1 upon PWM period. When TMR2 is equal to the PR2, the following three events occur on the next increment cycle. That is, TMR2 is cleared, the CCP X pin is set, exception if the PWM duty cycle equals to 0%, the CCP X pin will not be set. Third, the PWM duty cycle is latched from CCP-RXL into the CCP-RXH, lower byte into the higher byte. The PWM duty cycle is specified by writing to the CCP-RXL register to the CCP-X control register 4th and 5th bit. Up to the 10-bit resolution is available. The CCP-RXL contains the 8 MSBs and the CCP-X control register 4th and 5th bits contain the 2 LSB. Total, this 10-bit value is represented by CCP-RXL, CCP-RX control register 4th and 5th bit. The following equation is used to calculate the PWM duty cycle in time. So PWM duty cycle equals to CCP-RXL is to CCP-X control register multiplied by TOSC multiplied by TMR2 prescale value. So if we know PWM duty cycle, oscillator timer and prescale value, we can calculate the 10-bit resolution value. The CCP-RXL and CCP-X control register can be written to at any time but the duty cycle value is not latched into CCPRXH until after a match between PR2 and TMR2 occurs. That is, the period is complete. In PWM mode, CCPRXH is a read-only register. Then how to set up for the PWM operation? In PWM mode, CCPRXH is a read-only register. The following steps should be taken when configuring the CCP module for PWM operation. Set the PWM period by writing to the PR2 register. That is the first step. Second step, set the PWM duty cycle by writing to the CCPRXL register and CCPX control register 4th and 5th bit. Means 4th and 5th bit of CCPX control register. Third step, make the CCPX pin an output by clearing the appropriate TRSB bit. Then set the TMR2's prescale value. Then enable the timer 2, means start the timer 2 by writing to the T2 control register. And fifth step is configure the CCPX module for PWM operation. Let us take some example. Example 1. Find the PR2 value for the following PWM frequencies. Assume XTL equals to 12 MHz and prescaler equals to 1. We have to calculate the PR2 for the frequencies 12 kHz and 30 kHz. So formula for the PR2 is FOSC divided by 4 multiplied by PWM frequencies multiplied by N. N here we are considering 1. Put the values of FOSC 12 MHz and PWM frequencies. So for 12 kHz we are getting PR2 equals to 249, and for 30 kHz we are getting PR2 value is 99. Next example, find the values of registers PR2, CCPR, CCP1 RL and DC1 DB2 is to DC1 DB1 for the 1 kHz PWM frequencies if you want 50% duty cycle. Let us consider here, assume XTL equals to 10 MHz. Using PR2 equals to FOSC divided by 4 multiplied by PWM into N, we must set N equals to 16 for prescale. Therefore we have PR2 equals to 10 MHz divided by 4 into 1 kHz into 16 minus 1. So 1 we are getting 156 minus 1 equals to 155, and because 155 multiplied by 50% duty cycle equals to 77.5 we are getting. Now we have CCP R1L equals to 77 and DC1 B2 is to DC1 B1 equals to 10 for the 0.5 portion. Next example, write an embedded C program to generate a PWM waveform of 2.5 kHz and 75% duty cycle with prescale value equals to 4. Here assume XTL equals to 10 MHz. Let us see what we have. We have the crystal frequency 10 MHz, prescale value 4, PWM frequency 2.5 kHz, duty cycle 75%. The value to be loaded in period register 2, that is PR2, equals to formula we have to apply. So we will get the 249. For 75% duty cycle, the value to be loaded in duty cycle register CCPR XL equals to percent duty cycle multiplied by PR2 value. So 0.75, that is nothing but 75% multiplied by 249, we are getting 186.75. The 186 integer value and 0.75 value after decimal point will be loaded by the duty cycle bit from CCPX control register. So the value to be loaded in CCPX control is 0x3c 0.75 value after decimal point PWM mode of operation of CCP module. So put the values of PR2, CCP R1L, CCP1 control register into the program. So let us start with the program. First of all, we have to include PIC 18F4550 header files. Some configuration bits we have to set or reset here. Then let us start with the main function. First, we have to make RC2 pin as a output pin. So we have written TRISC equals to 0x00. Then next step is put the value into the PR2. The value which we have calculated 249 we have to put into the PR2. Then T2 control register prescaler value we have to select here, that is 4. So T2 count equals to 0x01. Then while 1 forever loop. Now next step to put the value in CCP-R1L and CCP1 control register. So CCP-R1L equals to 186 and 0.75 portion which we have to pass into the CCP1 control register, that is CCP1 CON con equals to 0x3c. Give some delay. Then TMR2 equals to 0x00. Load the TMR2 with 00H. Then clear the interrupt flag by writing PIR1 bits dot TMR2 IF equals to 0. Next, start the timer 2 by writing T2 con bits dot TMR2 on equals to 1. Then monitor the TMR2 interrupt flag bit while PIR1 bits dot TMR2 IF equals to 0. Then repeat. Thank you.